Dr. Ryan Parr began his research career at the University of Utah in the Department of Cellular, Viral, and Molecular Biology in 1980. He's participated in a variety of intricate projects such as nuclear differentiation within, I'm not even going to pronounce it, it's bad, mechanisms of viral infections and causes of lupus. Moreover, as a senior research specialist at the University of Utah Health Sciences Center in the Department of Hematology and Oncology, he works on the problem of cancer becoming resistant to drug therapy. One of Dr. Parr's major projects is the DNA sequencing of Egyptian mummies found in the Dekla Oasis, which has been in the news in the last few years. He worked on the mummy DNA and profiled in the PBS series Secrets of the Dead. His most recent work involves use of mitochondrial DNA to identify unclaimed victims from the 1912 RMS Titanic disaster. He's authored and co-authored many mitochondrial DNA studies of Native Americans, specializing in ancient DNA. Some of these studies include ancient DNA analysis of the Fremont Amerindians of the Great Salt Lake Wetlands, and ancient DNA methods, progress and perspective, and molecular genetic variations of prehistoric inhabitants of the Eastern Great Basin. Dr. Parr is Vice President of Research and Development at Genesis Genomics in Ontario, Canada. And before joining, he was Associate Professor of Anthropology and Co-Director of the Ancient DNA Studies at Lakehead University. He has over 20 years of research experience and has supervised 4 students in the pursuit of their thesis. He received his MA in Ancient Near Eastern Studies from Brigham Young University, his PhD in Biological Anthropology from the University of Utah, Salt Lake City. And he's one who does primary research in DNA, and we're very pleased to have Dr. Ryan Parr come speak to us.
Thanks, Scott, and I would like to thank the organizers of the conference for being invited to talk about 2 really great subjects, and that is the Book of Mormon and DNA, which, when you look at its structure and its design, is no less of a divine inspired molecule. I haven't even told a joke yet. We live in a very exciting age. Now, by the time you finish watching CNN, you may not think that. But there is a lot of good that's going on in the world today. And actually so this is sort of a public service announcement on DNA. But you'll often hear the word genome. And genome refers to the entire complement of genes that each one of us has. And for humans, that's between 30 to 80,000 genes. And this is really going to be the basis of an economic revolution in countries that will take note. In fact, Bill Gates has said that if he had the opportunity to do it over again, he would be in biotechnology, because with the early days of this type of research was pre-1995, they call the ancient days. And now, since we've actually looked at and deciphered the entire human genome, there are many things that we think we can now do. We can use DNA as a biosensor to detect, we're thinking, all types of diseases, cancers that now we treat after their clinical manifestations, long before there are clinical manifestations. So we really stand on a cusp and the threshold of a revolution, much like the antibiotic revolution of the last century. So they are exciting times. In fact, if you work in biotechnology and DNA, everybody's really excited to get to work to see the progress that's going to move forward. Whoops. And all this is really because of this molecule DNA. And DNA is really quite amazing because it just has 4 simple letters to convey its message. There's a G, an A, and a T, and a C. And with these 4 letters, everything about the human body is written in what we call the blueprints of life. Now that's pretty amazing because, of course, we have to use 26 letters to speak. But all of the information content held within the human body, and really responsible for the variation we see in this room when we look around us, is written in that simple genetic alphabet. Now, as we have deciphered the human genome, there's been quite a few surprises along the way. If you notice, there's all types of genes that we've found. There's the reality-based TV fixation, delusions of stock market savvy, and one I'm actually convinced is that fixation in my family. And fixation means that everybody has the gene. You can't escape. And this is just late-breaking news, but I think right here there's a Walmart gene. And this was affirmed by Businessweek about a year ago, who said that 80% of Americans made at least one visit to Walmart in that particular year. And it also comes in handy because remember, we used to, what was it, in the 70s, we used to blame our environment. And then we used to blame our parents for things that we didn't do, that we should do. And now you can blame your genome. So this really comes in handy. It's no longer, my parents made me do it, but my genes made me do it. Kind of like it's not your fault that mom married your dad. But along with this comes other challenges as well. And that is that there are DNA claims against the Book of Mormon. And most of these are based on modern population data. Number one, the genetic evidence of Native American characterizations does not support an ancient Near Eastern descent for Native Americans. Population genetics are consistent with Asian origins for Aboriginal groups. And I don't know if we should really be too concerned about this. It all lies in your expectation. And this is mostly based on mitochondrial DNA and Y chromosome, because in each one of us there's actually a paternal name that's written in your Y chromosome that you get exclusively from your dad, and in the mitochondrial genome that you get exclusively from your mother. So these actually turn out to be fairly great genealogical tools. That is, if you're just thinking in terms of a couple of generations. The more generations you receive, the more difficult it gets, and I'll show you why. So let's look at the claims behind this, and to do that we have to look at just a few basics to begin with. And that is, there are two great archives of DNA in the human body, or in the cell. There's this master library that is held in the nucleus. And this has billions of letters of information. If you take the information that you got from mom and you got from dad, there's 6.6 billion pieces of information. And the more we learn about this, I think the more astounded we are. We used to think that there were just genes and then long islands of nothing. But recently, within the last year, one of the big probably heard the word microarrays. A group that makes microarrays has done a lot of research and found out that these islands of nothing may not be nothing, but they are important for coding, they're important for turning genes on and off. And then we have out here what I like to term branch libraries. Out away from the central nucleus are these mitochondria. And mitochondria are very important. I think when most of us went to school, if you paid attention in biology class, they just said, it's just the battery. It powers the cell, and don't worry about it. However, that's changing quickly. Now, for the mitochondrial aspect, it's interesting because it has its own complement of DNA, but it's extremely modest in comparison to its nuclear cellmate. It only has 17,000 pieces of information. But these branch libraries are numerous. There's thousands, maybe 10,000 in a particular cell. I have to look at my notes to see if I'm not getting sidetracked. And so important is this molecule that the nucleus actually pays a tithing of 10% of its total complement to speak to the mitochondria. So these two speak back and forth, and they're in communication actually in just microseconds, nanoseconds. And that'll become apparent as to why that's so important. So, just for a rough comparison here, nuclear DNA, of course, sits in the nucleus. And it's the equivalent of about 50 sets of encyclopedias, so a lot of information. Mitochondrial DNA resides out of way, but it's still in communication. There's still phone lines, still email going back and forth in a chemical sense. That's about 10 pages of information. But these 10 pages of information are the same in every mitochondria that's in the cell. And so there's a certain number of volumes here that's important to make sure that mitochondria work. And the reason why that is because mitochondria are vital. I can tell everyone in this room your mitochondria is working, otherwise you wouldn't be here. Because it's responsible for generating 80% of the cellular fuel at a molecular level. In fact, we're now moving into a new phase where there's beginning to recognize that there are mitochondrial diseases. And many atypical diseases that we see now are going to end up being mitochondrial diseases. Estimates go as high as, incredibly high, that as many as 1 out of every 5 people may have a mitochondrial disorder. And that's because mitochondria, they code for actually 37 genes. Now, 13 of those genes, they're important because they make sure, or let's see, 20, it's hard to do math when you're in front of a group. But anyway, there's 13 genes there that are very important for energy production. They work in concert with signals that are sent down from the nucleus. And the other genes just simply make sure that these get made. So I think what I'm trying to say here, that maybe I should have said at the beginning, is that just simply looking at the population genetics and making a judgment as to what it means to a group of people from 2,600 years ago is very precarious, because this just isn't simply a genetic marker. It's vital for energy metabolism. So this is just a gee whiz figure, and you're not supposed to be able to figure it out because it's supposed to overwhelm you. With all of the metabolic pathways that's actually driven by mitochondrial DNA. So actually we found that when a cell develops pathology, for example, cancer develops, in some cases, it shows up early in the mitochondrial DNA in the form of alterations in this simple genetic alphabet. So now the claims are made against Y chromosome and mitochondrial DNA. So let's first of all take a look at the Y chromosome. So these have unique patterns of inheritance, and that is that they stay steady through a line. In fact, it's not surprising that some Jewish groups have a specific Y chromosome marker at a high frequency of about 50%. If you read the heavy paternal lineages, for example, in Chronicles, or if you've seen the home teachers, and where they put that tape in, and they go on Jehoshaphat, Jehosu, and whoever, that's literally true. Long histories of paternal chromosomes, and those can actually get fixed. But what happens is that dad has to have a son. Son has to have another son that has to be passed on. Now, if this dad here had a daughter, he doesn't pass on his paternal Y chromosome. That doesn't mean that he doesn't have a brother out here that doesn't pass it on. But this comes into a very important point called coalescence, where over time, most of these genetic signals can and do disappear. It's been proven from a statistical viewpoint. So we also have mitochondrial DNA, which we get from our moms. So actually, in mitochondrial DNA, there is, in the same paternal or Y chromosome, there's a maternal name written in these 4 simple letters, the G, the A, the T, and the C. And this occurs in a subset of the entire genome. So where the maternal name is written is usually very small. We call that the hypervariable region. And same game. So if mom has daughters, then this is passed on. If mom had a son right here, this isn't passed on. So I want you to keep this in mind, because this is very important when you start to talk about really small groups like Lehi's family, and you consider the 8 years that they were in the wilderness. statistically, you start to get problems with the frequencies that have been suggested. So how did these look? How do we actually read these? It's actually quite dull. So this is, and I just said that this was exciting, didn't I? So each one of these lines actually represents, you could say, a maternal name. This is actually sequencing data, what we call. You can see there's the G's, the A's, the T's, and the C's. And then down here, the software. And I should say that without the advent of computers, this would be impossible. And now many large companies like IBM are trying to get interested into these types of biosciences because there's so much information that needs to be decoded, and because of the coming revolution in healthcare, they see these as tremendous revenue generators. So one thing I forgot to mention, sort of the blue sky of all this, is that in not too distant future, you'll go into your physician and you'll swipe a card, and it'll say, okay, well, Scott Gordon back there, he doesn't respond very well to ibuprofen because he has this particular gene, but we know aspirin works for him. Ampicillin may not work for you, but we'll give you tetracycline. So all these things will become a very highly practiced type of science, and things will be treated long before they show up clinically because they'll be anticipated at the DNA level. So all this information is interestingly, once again, written in this code. But for our purposes here, so what happens if you look at this little dot right here? The software gives us this heads up and says, well, there's somebody here that doesn't match. So if you run up all these T's, we see, aha, there's a C right here. So this person actually has a different name simply because this differs by one letter of the genetic alphabet, and the same here. So you can imagine the problem with trying to handle all of this data when you're looking at populations of people that have billions of pieces of information. But what's important, I think, here is that most of the lineages can actually be the same, and most of them probably swamp this particular individual here. And this is a sampling of a large populations of people from Thunder Bay, Ontario, Canada. And this information, this maternal information, and also the Y chromosome, has been used to come up with various ideas, and this is really quite ingenious and very exciting. Is that there's been multiple migrations out of Africa. You probably all heard of the 7 daughters of Eve, and you can send in your DNA, and they'll tell you which Eve you came from, and Adam, and all that type of thing, which are interesting commercial ideas. But so from this, and the caveat is these are, once again, modern populations. So we can see that Native Americans really, scientists aren't very inventive because they have 4 maternal names, A, B, C, D, and X. That's not very exciting, is it? But it looks like, really, from areas here in Siberia, that many of the modern day signatures but they do match these people coming out of Siberia. And to a lesser extent, there are some haplotypes in Asia that match as well. But it's these major 4, and I think that's here's where the claims come that, well, geez, Native Americans have these haplotypes, and where are the ancient Near Eastern haplotypes when we look at modern DNA? But another important thing to notice is that there are different distributions of these haplotypes, and that's another thing that comes into play. So there are limitations to this approach, and this is never really brought out. But the huge limitation is this is based on contemporary data. And we'll look at some population histories later on here, and you'll actually see that there are many population histories that are written in Native Americans. And simply because all these names don't appear at this particular period in, for example, the Cherokee, doesn't mean that they weren't there in some time in the past. It doesn't mean that there aren't names that have gone to extinction, because there are a lot of variants, and we're just seeing, this is much like reading a Sherlock Holmes book. Well, not reading a Sherlock Holmes book, but reading the last chapter, and then from what's written there, trying to reconstruct all the nuances of the plot of a Sherlock Holmes book. That would be difficult. And mitochondria are much more than population markers. They're actually very, very dynamic. Sometimes we get the idea that genes don't move, that it's just what we, get that stays with us. But they can be dynamic, as we've seen with pathology, that you can get mutations, but that probably doesn't apply here. So let's go back to the beginning. The guy that's really responsible for all this, and that is Father Abraham. Just to illustrate some points of groups that move. So Father Abraham here started out from Ur. He came across the Fertile Crescent, and he ended up somewhere in Palestine. Now, what's interesting about this, and I think this comes into play with the Promised Land, is that when Father Abraham went to Canaan, he didn't go to Promised Land retirement villa. There were people there. There was opposition. So when you go to a Promised Land, it's just not like, go there and play golf until the second coming. That's not how it works. But from a population perspective, let's go back to the city of Ur. So this may be what the city of Ur looks like when Abraham was there. People are at the market, they're shopping for leeks, and maybe they're going to go hear a reading of the Epic of Gilgamesh that evening. But what I've done with Abraham is I've taken some of these people, I pulled them out. So if you think of the gene pool of all these people, I've taken a very restricted number, a kin-associated group. They've gone somewhere else. Now, just because you're Abraham and you've left your population doesn't mean that God hits you over the head with a wand and says, I'm going to change your genetics so you're unique. No, we're all pretty much like, for example, in this room, we all look very much European, and we would probably all be X, mitochondrial type X. So this is what happens to Abraham. So he leaves the area. And this is what we call a genetic bottleneck. There's just no getting around it. So if you think of a genetic bottleneck, think of I think I'd better thank Farms for this, because this is one of their articles, and I just chopped it up. But so you have an old-fashioned pop bottle, and you have variation in here that represents all the people. And then Abraham is going to leave, so you just pour a couple of these guys out. So you don't have what's representative anymore. You have a subset of this. So we have a genetic bottleneck already. But now let's step ahead 1,200 years to Jerusalem and to the outskirts, where we have a small kin-associated group, such as Lehi and his family, who've left for a promised land. And once again, this is a kin-associated group. So we've had Abraham in the land of Canaan. There's been population histories for that 1,200 years. We just don't know. So even probably the signal from Abraham is lost once again in the intermarriages that may happen. Maybe they all looked very consistently the same. This is the problem you run into if I was to run over to the ancient Near East today and say, let me look at these Israeli and Palestinian populations. This is what they looked like 2,600 years ago. It just doesn't work that way. And the literature actually is very cautious about that and says, we have to be very careful how we reconstruct these ancient lineages. So we have this kin-associated group, Lehi and friends, and they leave. So we have another bottleneck. And they're out here wandering around in the wilderness, And of interest there is that they're out there for 8 years. Now, there's things called infant mortality rates and that type of things. You don't have modern medicine, you don't have physicians, you just can't drive into the emergency ward, and if you're going to die, you generally die. So there's probably, again, genetic reduction that occurs naturally in these small kin-associated groups. Not everybody lives, not everybody has sons and daughters, and it's more acute in a small group like that. So they can tend to go to what, again, we call fixation rapidly. But probably it shouldn't have happened here because it was only 8 years. So when we travel to new lands, the things that we always take with us are our genes. So we take our nuclear DNA, we take our mitochondrial DNA, and it's all a certain amount of variation that comes along in a little cup. In fact, if you look really close, Sarah is holding this cup. But anyway, you are alive out there. So what happens, I think, well, let's not go to that yet. I just want to say a couple things about Promised Land. So we believe that they sailed over to Mesoamerica and landed somewhere in this area. And this wonderful graphic is courtesy of Blake and Joseph Allen. But let's talk just a minute about Book of Mormon and what it has as the Promised Land. I know that we all believe that they went to a land where there never was before man. At least that's our traditional understanding of what that means. But if you look really close at 2nd Nephi, I mean, I think it seems like sometimes we tend to get carried away. It's sort of written in covenant of Abraham language that says those brought out of the land of Jerusalem. So a very specific group of people. They'll prosper. They'll be kept from all other nations. They'll possess this land unto themselves. But the conditions always are that the laws and statutes are respected and lived. So the promised land idea is really associated with the covenant of Abraham and does not cover some of God's other children that are living in this new world. In fact, you can almost think of Lehi's group as a boat of missionaries. Why not? Bring the covenant of Abraham to a new land. And also, if you want to think in terms of like the saints that came into the valley in 1847, they certainly didn't come to a promised land retirement area. In fact, it was just the opposite. There were things that they had to do that built character, that let them become all that they were to become. In fact, Elder Maxwell always makes the point that these trials and tribulations that we are given are very specific for each one of us so that we can tutor, we can learn, we can become all that's intended for us in the divine sense. So we also look at Joshua and the children of Israel. They had a literal war on their hands, but nevertheless God told Joshua to be not afraid, neither be dismayed, but be of a strong courage, and I'll be with you in these ventures. So it seems like in the terms of Promised Land, there is opposition in all things. So they come into Mesoamerica, and according to Michael Crawford, at the beginning of the 15th century, and see now again here we're having to rely on modern data because that's all we have, he says that there were 25 million inhabitants in Central America. Those are a lot of people. So let's just sort of look at what John Sorensen calls Lehi's neighbors. I call this I was going to call it Shadows of the Empire, but I thought that had already been used. Shadows of existing people. And when we read in the Book of Mormon, it was never intended as a population history. But if you read it as that, there are really interesting clues and nuances. First of all, we find out it's repeated over and over. This is only a 100th part of the record. So those things that we think are important today, the genetics and so on and so forth, weren't even an issue. And if you've read the Book of Mormon, you can understand why. I mean, Mendel is still in the future, sort of the father of genetics. Watson and Crick, the discoverers of the double helix, in 1953, aren't even a thought. In fact, the bacterial theory of disease isn't even a thought. These people have other issues, and the issues seem to be social and political. What's really fascinating, I think, is some of the language that's used. So this sibling rivalry becomes very dangerous. Lehi is told by Revelation to leave. Well, he says, I'm going to take my relatives. And then he says, and those who would go with me. Well, who are these people? I mean, there are only so many people that came over on the boat. And he should know everybody. Temple construction takes a lot of manpower. So it's going to cause his people to be industrious. So the shadows continued. So what I try to do is look early on in the Book of Mormon for these clues and these nuances. This is what Jacob says, and you can't, it just turns out that Lamanites and Nephites isn't even a genetic term, and it's not anyway, because they all share the same genetic background. Jacob says this, he says, but I, Jacob, shall not hereafter distinguish them by these names, but I shall call them Lamanites that seek to destroy the people of Nephi, and those who are friendly to Nephi I shall call Nephites, or the people of Nephi. Interestingly, polygamy is no longer an accepted practice. So you're not going to have these huge Y chromosome incursions. And even if it was, there are not enough women from the ancient Near East to drive that genetic agenda. And then this one, I think, is very interesting. This was pointed out by John Sorensen. He talks about Sherem. So Sherem comes to see Jacob, and he says, Brother Jacob, I have sought much opportunity that I might speak unto you. For I have heard and also know that thou goest about much, preaching that which ye call the gospel, and that ye have led away much of this people. Well, come on, when I go to I know where my relatives live, don't you? So it seems like there were these collisions and these interjections with populations fairly early. And if we continue, some of these shadows, interestingly, Jerem, who's the son of Enos, who's the son of Jacob, says, and they were exceedingly more numerous than were they of the Nephites. And then there's always this missionary effort. And it came to pass that many means were devised to reclaim and restore the Lamanites to the knowledge of the truth, the Lamanites or those who do not believe. Alma the Younger and the 4 sons of Mosiah, for example, set off on a long missionary effort. And finally, when you go to 4th Nephi, neither were there Lamanites nor any manner of ites. So these divisions that we see in the Book of Mormon really have nothing to do with genetics, but they seem to be one large group. Okay, so let's look at our genes coming from Jerusalem. So you have these kin associate groups. You have, let's be generous and say there were 4 mitochondrial lineages, there were 3 Y chromosome lineages. So you dump these guys into the gumball machine, we'll make A, B, C, D, and X all the same, and then you dump these guys in. And one of the things that we find right off is that if you brought some of these genes from Jerusalem, you're not going to fare very well in this new environment. It's like wanting to be a basketball star, but not being able to dribble or shoot or run. And that is that the way mitochondrial DNA is distributed in populations has to do with what we call selection. So if you can't run, jump, or shoot, jazz are not going to ask you to come and try out. And the same thing again.
natural selection shaped regional mitochondrial DNA variation in humans. And it's very, I think, instructive that in these migrations that we see, we only see a select number of mitochondrial DNA names, A, B, C, D, and X. In ancient history, I think we have to suspect that there were many of these that just went out of existence. And there's this other issue that's called coalescence or lineage sorting. So let's look at this. So these nodes at the top, these are 18 women, and we're looking at the first generation. It doesn't matter if these are actually women or men, but what happens is you look at the lineage scenario through the generations, and this is 20 generations, or 500 years. This person, this woman, had no daughters. And we're supposed to assume that all these are unique mitochondrial lineages. And so it's even worse if this is strung out across the room where many people have the same lineage, and then there's just a couple that have these lineages that are probably at a selective disadvantage. What happens is that through time, things coalesce. There's this lineage sorting process, so that when you get down to the bottom, there's only 2 of the 18 that made it, 11%. Now, these are just population facts, whether or not you're God's people or whether or not you're Nephite, Lamanite, or whateverite you may be. There is a sorting process, and that's based on the idea that these molecules here are the same. Well, you have some, you're outnumbered, you're at a disadvantage because you can't run, jump, and shoot like everybody else. And so there is actually this funnel, this sieve sort of process that takes place. And if we look at the current people that live in Mesoamerica, you can see this very well. So you have your A, B, C, and D, and various populations here. But you can see, for example, like this group has A, it has B, it has C, but where's D? It doesn't mean that 300 years ago they didn't have D here. So what I'm trying to say is that, and it's the same for all these, you see a population history written in every one of these people. And we're seeing the buds on the tips of the trees. We're not seeing the branches, we're not seeing the trunks. So everyone, I mean, for example, this one, this group of people, they're missing 3 of these. This one probably is not fair. This is Caribbean, so they're probably islanders, which means there's more of a reduction yet. So, and I think this also speaks of selection once again. So why wouldn't all these be at the same frequency? Now, if we want to look at the way we do genealogy, say I'm right here, and I want to move back a couple generations, we can see that every generation, and now I should say I'm talking about nuclear DNA. I'm not talking about mitochondria or Y chromosome. But at every generation receding, your number of ancestors doubles. Now, when you get back so many generations, a lot of people, I mean, I have people tell me, you know, in my war at home, well, I'm related to so-and-so, the King of France back in 1400. Well, you may be related to the King of France because there's one of these lines that comes your way, but you're also related to everybody else. You may be related to Siegfried here that was thrown in jail. You may be related to so-and-so here that was a bank robber. And so there's a lot of people that you become related to. And the chances that your DNA, their DNA is in you, very, very small. It's like winning the lottery. And once again, that's just the population genetics. So this is really called the law of increasingly remote and genetically irrelevant ancestors. I don't make this stuff up. Then another interesting note that I think has been forgotten, and this comes from the Dakhla Oasis. There is a Romano-Coptic Christian site here in the Dakhla Oasis. And it looks like the people were proselyted. Coptic Christian just means Egypt. And there was a time when the early Christian movement moved throughout Egypt and proselyted people in their native tongue. And these oases exist as big footprints out in the sand on the west side of the Nile, which is kind of interesting in and of itself. If you're Egyptian, why would you live out in the West Desert? Because that's the land of the dead. Who wants to live out in the land of the dead? But anyway, they did, and here's a view of the ancient town of Kelis. And if you can look off to, I believe this is the east, there's the desert escarpment that moves up. These are sand dunes, and then here's the town of ancient Kelis. Well, in Kelis, there's a cemetery called Kelis II. Kelis II is very interesting because they buried everything. They buried stillborn, they buried children that died, they buried fetuses. And so we really get a look at ancient population demographics. And what's interesting when we want to think of the Book of Mormon and trying to push these genetics from the ancient Near East up through this population is that the pre-reproductive mortality rate is 63%. So over half of your children don't make it to have more children. And, you know, a lot of these, they were Christian. They believed in God as well. So God isn't selective among his people. We're sent here. We have to put up with the physical facts. So there you go. There is another genetic bottleneck. So I think from all this, I would like to conclude that these small kin-associated groups that we see in the Book of Mormon are at genetic disadvantages. There were large indigenous populations in Mesoamerica, 600 BC, and the Book of Mormon populations assimilated into the ancient genetic topography of Mesoamerica with these mitochondrial haplotypes A, B, C, D, and X. So do Book of Mormon people have the same mitochondrial haplotypes as Native Americans? Yes, they were assimilated in, but they were a small part that were participating in this in a specific geographical area. And once again, I think the really important, in sort of our, science always thinks that it has all of the answers right now. But we always live in an age of ignorance. And that is assuming that these current population data are adequate for this test. They're just simply not. I think if you were to be intellectually honest with yourself, it just isn't possible to really reconstruct these. What you'd have to do is you would have to find a cemetery where Nephi and everybody was buried, and then do ancient DNA analysis on those individuals. But it looks like fairly quickly this population was eclipsed. And this story wouldn't be different for any of us that would move into a large foreign population. I mean, pretty soon our kids start talking like so-and-so, start acting like so-and-so. There's only a certain number of people you can pick to be married to. And if they did stay together, then you have a lot of problems with recessive alleles starting to pair up, and there's a lot of genetic problems with that. And finally, I like this particular quote from Elder Maxwell. He says, "Because the editing of the Book of Mormon with its witnessing gospel of hope occurred under divine direction, it has a focus which is essentially spiritual. Yet some will criticize the book for being what it never was intended to be, as if someone could justifiably criticize a phone directory for lack of a plot." And for all intents and purposes, that's what we've been doing. So I guess from a personal note, am I saying that we won't ever find ancient Near Eastern genetics? No. I think there are some tantalizing papers now that suggest that there may be European input, I would say at this time, into these ancient populations. But I'm not that familiar with that information, so that's a subject for future study. And overall, the genetic differences in the human family is pretty slight. And so when we all say and speak of God's children, we are all very, very closely related at a genetic level. And here we're talking about very, very small nuances and differences when we talk about A, B, C, and D and X. So I think that, we need to see in sacred scriptures its full intent and its possibilities, and not really look for its limitations. So really, mercifully, the blessings of God and the atonement, they don't have genetic constrictions. And how could they with a all-loving God? We're all his children, operating under the principle of free agency, and the whole idea is whether or not we accept or deny that fact. And one final item is that I think that we as Latter-day Saints are too willing to accept what science or what critics have to say. We really need to be thoroughly skeptical of skeptics and critical of critics. Sometimes we are very gullible in our faith. If the boy Joseph saw Jesus Christ and God the Father in the grove, what do these criticisms really matter? That is the major fact. And so I would like to leave that with you, and thank you once again.
Answer whichever one you want.
I don't understand this. I think that the icon should work, right? Can you comment on the DNA research done by Simon Southerton, who states Simon Southerton has written a book called Losing a Lost Tribe, DNA, the LDS Church, so on, and so forth. For the reasons that I outlined here, that book is very problematic because once again it looks at population frequencies. In fact, the one graphic that I did show showing current population frequencies, if you notice, the note at the bottom was actually from his book, but that's a compilation of all the data that's out there in the literature. Suffers from this same, I hate to use the word myopic, but you just can't look at modern populations and say this is how it was 2,600 years ago. Population histories are really complex, and many of the experts in this field say we can only hope to understand the very outlines of what happened and what went forth. So, yeah, in other words, could I be a descendant of Lehi and yet have none of his DNA? That's a very good question. I think we all have this same sort of problem when we do our genealogy. And again, on a DNA basis, we're all very closely related. And I think we're making Mount Everest out of speed bumps. Could I have none of his, and I mean, I didn't mean that in a rude way, and yet have none of his DNA? I don't think God cares about DNA. If once again you consider the covenant of Abraham, he says that all of the nations of the world will be blessed. How could that be genetic? If we're all created in his image, and if you look at DNA, it's this divine, sculpted molecule that's incredible. We are his children. If you want to have to claim that you're from Lehi or so on and so forth, to me, from my perspective, that's not, I don't know. I mean, my ancestors could have fought at the Battle of Hastings in 1066. I would be very thrilled if they did. Well, sheesh, they would have had to have made it, didn't they? They couldn't have got killed. But I'm still probably have none of their DNA in me.
So it's possible to have none of his DNA, right?
It's possible to have none of his DNA, but you could have one of these lines coming down showing that you are a direct descendant. But remember, you're related to all of the other people in line as well. Am I done?
Try one more. Just
Okay.
We've got a couple others too. You kind of glance through and see what you like.
Okay. Oh, this is a good question. The African tribe, the Lemba, have been easily shown to be descendants of Hebrew migration. They also heavily intermarried with locals. What is different with Lehi's migration? That's a very good question. First of all, once again, we don't know the nuances behind that genetic migration, and that's based on Y chromosomes. And there were heavy Y chromosome populations. Once again, if you read in 2 Chronicles, these men had multiple wives, and all they list are the sons. And so what's interesting about the Lemba is they have those chromosomes, but they also have African chromosomes. So the time schedule there may be different. Say they had 50% had Y chromosomes that were Jewish, and 50% didn't. That says to me that these groups are going to fixation in another direction. And if you look at them, they look Afro-American. I mean, African, excuse me. They look African. So, I mean, you can't say that there isn't this integration taking place. And once again, we don't know. I mean, if there were multiple migrations into this area, and I'm not an expert on this, then you get this genetic reinforcement, sort of like, at the beginning of the last century, we always hear the story of the Titanic and the White Star Lines. Those ships were actually built to carry immigrants to the New World. And that's what I'm saying. Here we have this reinforcement from Europe, and we simply don't know what happened to the Lemba. Was there a trail where people continued to go there? So yes, they do have this Hebrew look, but physically they don't look that way, and half of them genetically aren't. So are you going to say that those half that don't have those markers are not Abraham's children? So this is where we really run into problems. And the difference with Lehi's migration is that Lehi's is a small kin associated group, and they're in collision with a large population. And so those are sort of the things you have to consider.
Thank you very much.
Okay.
I'll give you those just so you have them.
Oh, okay.
Souvenir.
Sorry.
You can.